Duality is one of the most important concepts for linear programming. We're going to take a look at this in 2 videos. This video will be an introduction to duality, and then in the next video we're going to prove the strong duality theorem using Farkas lemma. But let's start with introduction, and for that let's start with an example. And our example here, we have the following linear program, and what we would like to do is derive upper bounds on the objective value. So can we use constraints to get an upper bound on the objective function? And let's simply start with the first constraint. So only using the first constraint can you upper bound the objective function. So we can, how we can do this is we see 4 is larger equal 2, 8 is larger equal 3. Now, since the variables are non-negative, we have that 2x1 plus 3x2 definitely has to be smaller equal to 4x1 plus 8x2, and there we have the upper bound of 12. Can you do this even better? Again, let's say just using the first constraint. Yes. So obviously 4 and 8 are larger than 2 and 3. But so if we divide all of this simply by 2, then we have 2 and 4 and 6. And that's still an upper bound. So our objective function we can bound by 1/2 times the left-hand side of the first constraint. And that's then smaller equal 1/2 of the right-hand side. So we now already have a bound of 6. We would like to improve this further. And let's say for this we allow ourselves to use the first 2 constraints. So can you take the first 2 constraints and get a better bound than 6? What can we do? If I add up the first 2 constraints, 4 plus 2 is 6, 8 plus 1 is 9, and now if I divide this by 3, I get a 2 here, 9 by 3 is 3. So this actually tightly bounds the left-hand side. So 2x1 plus 3x2 is smaller equal 1/3. And this is now the sum of the left-hand sides of the first 2 constraints. This I can bound by 1/3 and then the right-hand sides. So 1/3 of 12 plus 3. So 15 divided by 3 is 5. So now we already have a better bound of 5. Of course, we are interested in whether this is optimal or whether we can do it even better. And let's make this more precise and formalize what we were doing here. And then we can also bring in the third constraint. So what we were doing here was we wanted to derive from the constraints an inequality of this type. d1x1 plus d2x2 is smaller or equal to h, where d1 had to be at least the 2 that we have here, d2 had to be at least 3 because there was a 3 here, and we want to have h as small as possible. So if you want to have h as small as possible, that already sounds like an optimization problem, and it's an optimization problem that we can solve using a linear program. And the idea of this linear program is now that we can use variables to decide the coefficients for each of the inequality. Previously what we did, we took 1/3 times the first inequality and 1/3 times the second inequality and added that up. But more generally, we can take coefficients y1, y2, y3, and then we take y1 times the first inequality, y2 times the second inequality, y3 times the third inequality, and this looks like that. So we have y1 left-hand side plus y2 left-hand side of the second one, y3 left-hand side of the third one is smaller equal, and then we have the right-hand side, so 12 times y1 plus 3 times y2 plus 4 times y3. If we now reorder these terms, then we have this here as the coefficient for x1 and this for the coefficient of x2, and this being smaller equal to that number here. So going back to that, we would like to have a bound like this. We want to find d1 and d2 such that d1 x1 plus d2 x2 smaller or equal h. d1 had to be at least 2, d2 had to be at least 3. This means that my d1, which is this, we want to have that is at least 2, and my d2, which is here, it should be at least 3. And we want to minimize this term. And now we have a linear program to determine my coefficients here, the y1, y2, y3. So we want to minimize h subject to d1 being at least 2 and d2 being at least 3. And this is called the dual linear program for this one. If we now would solve the dual linear program, let's say using the simplex method, it would give us an upper bound on the objective value of our original linear program. So let's say we would actually do that and we would get a solution. So interestingly, actually the upper bound that we get is tight. So the dual linear program would give us a 4.75. So that's better than the 5 that we saw previously. But also the primal LP, so the original linear program, if we actually solve it using the simplex method, let's say, we get as optimal solution 4.75. Here are once more the two linear programs. If you inspect them more carefully, you will notice a bit of structure. So the coefficients 2 and 3 here, they show up here on the right hand side. The right hand side of the primal linear program shows up as coefficients of the objective function of the dual linear program. And now finally, if you look at these coefficients here, and think of it as a matrix, so your matrix here is 4, 8, 2, 1, and 3, 2. Yeah, you see this matrix back here, but transposed. So here we have A, if we call this one A, this is A transposed. So more generally, if we have a linear program in this form, so maximize something subject to ax smaller equal b with x non-negative, then the dual linear program will be minimizing. Now we have b transposed y, so the right hand side from here, subject to a transposed y larger equals c. C was the coefficient vector for our primal objective function, again y non-negative. We motivated duality by the goal of getting an upper bound, and this is what the weak duality theorem also states. So if we have feasible solutions for the primal linear program and for the dual linear program, and then look at their objective functions, so for the primal linear program that was c transposed x, for the dual one it was b transposed y, then this b transposed y gives us an upper bound on c transposed x. So this is weak duality. Also, if the primal is unbounded, then from this it follows. So if this becomes arbitrarily large, then obviously here I don't get a solution, so then the dual is infeasible. Likewise, if the dual is unbounded, because it's a minimization problem from below, then the primal is infeasible. So let's prove this inequality. So we have c transposed x, we want to bound it by b transposed y. So we will first use the dual constraint. So in the dual linear program we have this constraints. A transposed y should be larger or equal c. So I can take that here, c transpose. So c I bound by a transposed y, so we have c transposed x is smaller or equal a transposed y, that's from here, transposed x. Now, okay, I actually transpose this, and the primal program has the constraint ax smaller or equal b. So if I plug this in, I have y transposed b here. I wanted to have b transposed y, but this is actually the same. So I mean, what I have here is a row vector and a column vector, and I multiply them, and that's the same as taking this column vector, making it the row vector, and the other one making it the column vector. So let me show this So here, y transpose b, this is here, and this simply gives me the sum, which is the same as if I do b transpose y. So this is weak duality. But actually something much stronger holds. This is a strong duality theorem, and that states that if there's a solution, then the optimal feasible solutions for x and y actually satisfy this with equality. So we already saw in our example that actually the primal and the dual program gave us the same value for the solution. And what the strong duality theorem tells us is that this was no coincidence. But proving this is a bit more work, and we're going to do that in the next video. For now, we just take this for granted. As a first application of duality, let us consider the following question. How difficult is it to find an optimal solution versus how difficult is it to find a feasible solution? So in previous videos, I already argued that this is essentially the same in terms of difficulty, but duality will allow us to make this more precise. So let me first come back to previous arguments that I gave, which are not completely satisfactory, but the duality will give us a very nice argument that this feasibility and optimality essentially are same problems, or at least of same difficulty. So one argument for that feasibility and optimality is equally difficult is that if I'm able to determine feasibility, then I can use or binary search to find an optimal solution. So what I mean by this, so let's assume I have a feasible solution here for a certain value of the objective function, and then for another value of the objective function I know that there's no feasible solution, so this is infeasible. Then I can use binary search to try to find something that is arbitrarily close to the optimal solution by simply going here. So this is the line with x1 plus x2 equals 3. So as a constraint, I can put in x1 plus x2 larger equal 3. So this would give me this polytope. I check, is there a feasible solution? Does this LP still have a solution? If yes, then I know I can continue looking for larger values. If no, I know that I have to look for an objective value smaller than 3, and with binary search I can get arbitrarily close to the optimum. Another argument that we had is the following. So in the simplex method, we had the first step of finding a basic feasible solution, an initial basic feasible solution. And the best idea that we had there was to use an auxiliary problem, so to solve an auxiliary LP, and that would give us a feasible solution to our initial LP. Yeah, so here we reduce the problem of finding a feasible solution to finding an optimal solution to the auxiliary. So this links feasibility and optimality. Doesn't quite tell us still what we wanted to know here, but duality does. So here we have our primal LP, the dual LP, and the weak duality bound. Now we can combine all of this into one LP, which will result in a linear program such that any feasible solution is optimal. So let's start with an initial primal LP, but as variables I don't just have the x but also the y. My initial LP had simply ax smaller equal b, but my variables also not only include x and y but also y, and I then also add my dual constraints, and I add this constraint here, which together with weak duality, so weak duality I get for any solution, but I know for the optimal solution I have equality, and I can enforce this by adding this constraint. So if this constraint is fulfilled, then I have equality here, and then I know that I have an optimal solution. Yeah, this means that any solution to this LP, any feasible solution to this LP, gives me an optimal solution for my original. And with this, you can say that feasibility and optimality are equally hard. So far in this video, we looked at linear programs where we had here a smaller equal and we had non-negativity constraints. Next, we want to generalize this. So for instance, what happens if I have equality here, or what if there are no non-negativity constraints? So I'll just give you this as a list. And after doing so, we will look at a physical interpretation of duality. But let's first do this recipe here. So far, we had linear programs in this form with a smaller equal here, non-negativity constraints, and the dual looked like that. Now we want to see what happens if, for instance, we have equality and so on. So first of all, we always have this matrix A. It has size m times n. M is the number of constraints, n the number of variables in the primal, and in the dual we have instead A transposed. So the n variables in the primal will give me n constraints in the dual. The m constraints in the primal will give me m variables. Beyond that, we get the following. So here we have our n variables, and in the dual the m variables. The matrix in the primal A is then A transposed in the dual. The right-hand side B shows up here in the objective function as the coefficients in the objective function, while the coefficients are in the objective functions for the primal will show up as a right-hand side in the dual. Then a smaller equal constraint in the primal will lead to a non-negativity constraint in the dual, while a larger equal will give me essentially a non-positivity constraint in the dual, while equality will simply give no constraint on the dual variable as such. Similarly, non-negativity constraint gives me a larger equal here. If I would have a non-positivity constraint, this would give me a smaller equal, and if I don't have a constraint on the xj on the variable here, this will give me a constraint with equality. You have to be slightly careful here. If you look at these three here, then essentially this, let's say the sign is inverted, or a smaller equal gives me a larger equal a smaller equal. Here it is not the case. So here larger equal gives me again a larger equal, smaller equal, stays again smaller equal. That's something to keep in mind. So let's see this by an example. So if we want to now maximize C transpose X, we still have a smaller equal here, but we don't have the non-negativity constraints. So what is the corresponding dual program? So what we have to look at is we have no non-negativity constraints. So this means we will have equality. A transposed Y equals C. And because we had a smaller equal here, we will have a larger equal there. Let's do another example. Here's our primal. What does that translate to? So here we had maximize. Here, of course, we have minimize. What do we want to minimize? For that, we have to look at the B here, and then we will get 4y1 plus 7y2. Then here I have A times X. There I get then YA transposed. So these values will flip. Let me show that here. So I have the 4, 7 up here, the 2, 1, and 0, 1, minus 1, 3. You'll find here 2, 1, 0, 1, minus 1, 3. And then the C that you see here will show up here. And beyond that, we have a non-positivity constraint on x1. That gives me a smaller equal here. We don't have a constraint on x2, so that's why I have equality here. Larger equal here translates to larger equal over here. And then beyond that, because of the equality here, I get no constraint on y2. And the larger equal gives me a smaller equal there. In the last part of the video, we want to take a look at a physical interpretation of duality, which in particular gives us a physical proof of strong duality. For that, we're going to have a prime linear program in the form given here, so smaller equal, no non-negativity constraints, and since we have no non-negativity constraints in the dual, we have equality here. And now let's take a look at the set of feasible solutions. Let's assume if we would have, for instance, 3 variables, then the set of feasible solutions would be a 3D polyhedron, or if we only have 2 variables, 2D polyhedron, or if it's bounded, 3D polytope or a 2D convex polygon. So, and now let's assume that the C from the objective function actually points downwards, so we can interpret it as gravity. And further assume we ask a feasible solution. Any feasible solution we see as a ball, which we can then drop within the set of feasible solutions. And gravity will now pull this ball down into the optimal corner. So likewise here, I have a ball, this is a feasible solution, but because of gravity, it will end up in this corner. This solution, so the optimal solution, we now call X star. The first two observations, or the first observation that we can make about X star is that it's actually it's in a corner, which in particular means it is on those 2 lines. Those lines are constraints in our primal linear program. And what we can conclude here is actually that if I plug in the optimal X into this line equation, then this is actually, because it's on the line, an equality. So here A1 transposed, simply the coefficients in the first row of A, which corresponds to the first constraint, and now multiplying that with X star. For any feasible solution, we have smaller equal b, and because I'm actually smaller equal b means on the line or above, but because I'm on the line, I actually have equality here. And likewise, let's assume this is simply A2, then I also have this with equal. So that's the first observation. Next observation, and this is now the physical interpretation. Here I have a force pulling it down, C, but since the ball stays here, I have an equilibrium of forces, so I have forces keeping that ball there, and this comes from a force on that side and that side, and the sum of forces on the ball should be 0. And these are vectors orthogonal to these lines corresponding to A1 and to A2. Now let me write this slightly differently. Instead of having these forces showing upwards, I will take the minus those forces, and those then actually point downwards, this one and that one. But then instead of having C plus those forces being 0, I would have, there are forces here such that C equals the sum of these forces. Yeah, this is now the minus the actual forces that bring us the equilibrium. And those 2 forces, they come in with certain coefficients. Let's call those coefficients y1 and y2. The equilibrium of forces allows us to conclude that C equals y1a1 plus y2a2. And let me once more say, so why a1 and a2? Because if this is a line equation for that line, and I have the orthogonal vector here, then the orthogonal vector is exactly this one here, or that transpose. So that is A1, so that's why I have A1 here, and I have the equilibrium of forces tell me there are coefficients here such that this adds up to C. Now, of course, we have other constraints, so this constraint here, but there are no forces. So overall, we can say that C equals the sum of the yi ai, where for everyone else I have yi equals 0, which corresponds to the fact that there are no forces from that side on the ball currently. But if this statement holds, then this is exactly what we need for y to be a feasible solution of the dual linear program. But there's something very interesting happening here, and that we can see by the following equation. So what we have here actually is that y transpose, so this is now the solution that we got for the coefficients of the forces, y transpose times ax minus b is 0. Why is that the case? Because I have this either, so for these constraints that are not involved, yi is 0, or for the one that are involved, I have that ax minus b is 0 because I'm on the line. And what I get from this, if I rewrite this, I get that, so let's take b times y transposed on the other side, then I have b transpose y, which is the same as y transpose b, equals y transposed ax, and y transposed ax. So y transposed a, we have here is the same as a transposed y transposed. So I get c transposed here. So what I have here is b transposed y is c transposed x, and this is exactly strong duality. So this gives me a physical interpretation of duality, which tells me that strong duality is true. We will see in the next video actually a mathematical proof, or I'll sketch a mathematical proof for strong duality. But before wrapping up, there's another interesting observation here, and that is the following. So we had an optimal solution for the primal and then also for the dual here, and it had the following property. Either yi was 0, so for any I, either yi is 0, or the corresponding component in ax minus b was tight in the sense that, so either yi is 0, or if it's not, then I have ai transpose x equals b. So here we have zeros, and here I'm actually on the lines. And this is called complementary slackness, and it's a characterization of optimality. The solution is optimal exactly if we have this, and depending on which form of LP we have, so there's also a version with non-negativity constraints. And why slackness? Because here what I have is that there's no slack. So either yi is 0 or there's no slack in the corresponding constraint.